Hi, my name is Daniel Manuel, and this is Lab 4. Introduction. The purpose of this lab is to understand the effects of resistors in series and parallel. We will use multimeters to measure potential differences in conventional current and model the behavior of capacitors and ohmic resistors. We will be using a FET-Lab to simulate all of these components virtually. Fundamental principles. Ohm's law. Voltage is equal to current times resistance. Capacitance. Charge times voltage is equal to capacitance, the node rule. Current flowing in is equal to current flowing out, loop rule. Total potential difference around an entire circuit is equal to 0. Part 1 procedure. First, we had to create a circuit with two 1.5 volt batteries, a 47 ohm resistor, a 100 ohm resistor, and two ammeters. The predicted current that we got was 0.0204, and the actual current is the same at 0.02. If we reverse the ammeters, it is going to be negative 0.02 for the current. The formula that we used for that is current is equal to voltage divided by resistance. Open circuit. We replaced the second ammeter with a voltmeter and expected a reading of 3 volts because of the 3 volt potential at the battery end and a 0 volt potential at the resistor end. The actual reading from the voltmeter was 3 volts as expected. Potential differences. I'm going to go through the potential differences that we got for each of the nodes. For BA, it is equal to 3 volts, CB, 0 volts, DC, negative 0.96 volts, ED, 0 volts, FE, negative 2.0 volts, GF is equal to 0 volts, HG is equal to 0 volts, HA is also equal to 0 volts. And if you sum up these potential differences, 3 volts, negative 0.96 volts, negative 2.04 volts, you get 0, which supports the loop rule. Ammeter in parallel. If we place the ammeter in a parallel to the 100 ohm resistor, then the current increases from 0.02 amps to 0.06 amps. This is due to the circuit being parallel with the ammeter, so less current encounters the 100 ohm resistor. Calculating resistance. To do this, we have Ohm's law, which states that delta V is equal to current times resistance, or resistance is equal to change in voltage over resistance. For the resistance of the 47 ohm resistor, we get 48 ohms. For the 100 ohm resistor, we get 102 ohms. For the resistance of the wire, we get 0 ohms. And for the resistance of the ammeter, we get 0 ohms as well. 0 resistance is in the wires or the ammeter. Part 2 procedure. We had to construct a circuit containing a 9 volt battery, 0.2 farad capacitor, 10 ohm bulb, and a 20 ohm bulb. Capacitor behavior. Charging times. So in the top image on our right, this simulates charging, and we get 10.8 seconds for a 10 ohm capacitor, and we get 19.2 seconds for a 20 ohm capacitor. That's how long it took for the capacitor to charge. And we could tell this because the brightness of the bulb went from fully lit to dim and then completely off. The maximum current is at first when the bulb is brightest. When the capacitor is fully charged, there is no current. Discharging times, the bottom image. For the 10 ohm bulb, we get a 13.2 second discharge. 20 ohm, we get a 27.3 second discharge. Maximum current is at first when the bulb is brightest. When the capacitor is fully discharged, there is no current, and the current flows in the opposite direction as during the charging. Here are our tables and graph that we use to calculate the capacitor time constant. We got a constant of 7.04 seconds. What if? What if you're doing this lab in real life and use an actual ammeter instead of an ideal simulated ammeter? What's the difference about a real emitter, and how would it have affected the circuits you hooked it up to? An emitter used in real life has resistance, unlike what we proved earlier in the lab. What if you were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor to reach full charge? Would this happen in real life? In an ideal world, the capacitor would be charged instantly, but in real life it would take time to charge since everything has resistance. Thank you.